So the title of my seminar is How to Build Pseudorandom Functions from Public Random Permutations. You can hear me, right? It's okay? Okay. So this is a joint work by Aaron Labroge and Bachmann. Okay, so we know that pseudorandom permutations and pseudorandom functions, or PRP and PRF, are the two of the most fundamental primitives in cryptography. And in the seminar work of Ruby and Rakov, they propose a way to design a pseudorandom permutation for a pseudorandom function. So their idea is modified by the DES block cipher, where they use R round of Faisal network. And it can be shown that 4 rounds is sufficient to get birthday bound security. But very soon people will realize that actually they need the opposite construction, which means constructing a PRF from a PRP. So the reason for that is because PRPs are usually easier to design than PRFs, and there are many of the well-analyzed PRPs in the world, such as the AES block cipher. So in the last few years, many of various of approach to turn a PRP into a PRF have been proposed. For example, the Sum of Permutation by Berari et al. In 1998, the Encrypted Davies-Meyer by Goshigadi and Chen in 2016, and Encrypted Davies-Meyer Dual in 2017 by Mendes and Davis. So, as you can see on the pictures, those constructions only evaluate the block cipher in the forward direction. Well, usually a block cipher is designed to be efficient in both the forward and the inverse direction. So, yeah, this makes block cipher actually an over-engineered primitive for this PRF construction. Now, sparkled by the SHA-3 competition, which is announced in 2007, and with its winner, the COSIC construction in 2012, where COSIC is a permutation-based hash function, and it led to an increasing interest in the construction based on public random permutations. So for public random permutation, it's usually very fast in the forward direction, but not necessarily very fast in the inverse direction. So this should actually be the complete picture where we consider the PRP, PRF, and public random permutation and public random function. So as already mentioned before, we already considered the conversion between PRP to PRF and PRF to PRP. So the conversion between RP and RF can be considered using the similar technique, where where actually the resulting function is keyless, and we assume that the underlying primitive is ideal. So then we can prove the security of this construction in the indifferentiability framework. So from RP to RF, it's usually considered the indifferentiability of some permutation, and from RF to RP is usually the indifferentiability of the Faisal cipher. So in the past years, lots of research have been done on those ideas, so I'm not going to explain too much here. So I think it's quite clear why it's not so interesting to design RP and RFs from PRP and PRFs, because that's quite useless. And so now, so the only interesting is to design a PRP or PRF from RP or RF. So the first case is to design PRP from a random permutation. This is done by the Even-Mansour cipher or the key alternating ciphers. So Even-Mansour cipher is proposed in 1991, and the key alternating cipher was proposed by in 2012, which is actually the iterated Even-Mansour cipher. And recently, in 2016, Huang and Cesaro showed the tight security bonds of the key alternating ciphers. And the next case is the design of PRP from random functions. It's done by the key alternating phasal ciphers, which is proposed by Gentry and Ramzan in 2004, where they combine the idea of phasal network with the Even-Mansour cipher, and it can be shown that full runs is sufficient to get perceivable security. And the way to design PRF from RFs is done by Gauzy and Cesaro, and they propose the following construction to design a pseudorandom function from random public random functions. Now, so the only open problem at this moment is how to design a pseudorandom function from a public random permutation, which is actually the title of this work. So to formulate the security definitions more precisely, we are going to consider the following attack game. So at the beginning of this game, one of the two roles is chosen. So the left side is the real one, and the right side is ideal one. So the adversary A is gets one of the two rules, and he can make Q construction queries to the construction oracle and P primitive queries to each of the primitive oracles. So in the real world, the construction oracle is actually the proposed construction, while in the ideal world, it's actually a random function. While in the primitive queries in both worlds are actually the same. So it's just an underlying primitive. So after communicating with the given oracle, A should state which of the two worlds it was given. So if A cannot do so, then we can say that proposed construction is actually a good pseudorandom function. So the first result achieved in this paper is by considering a general PRF design using one pseudorandom permutation call. And also using linear pair and post-processing function L1 and L2, so those two things. And we showed that this construction in general cannot be secure beyond Perceval bounds. In our paper, we propose different variants of the linear processing function and derive attack in the Perceval bounds or even faster to break all the variants. So here we are only going to discuss about the most general case. So this is the case where all the inputs to L1 and all the inputs to L2 have influence on the resulting construction. So for more details, you can see the paper. But anyway, so actually to break the thing in the Perceval bounds, it's very easy. You just need to find a collision of the input M of the construction query with the input X of the primitive query. As long as this collision can be found, then we can see that there will be a relation between the output Y of the primitive query with the output C of the construction query. Then we are able to distinguish the real construction from ideal. So now, we see that we cannot achieve beyond Perceval security with just one permutation call. So we're going to consider two permutation calls now. So instead of just designing a PRF using RP, we can first design a PRP using RP and then use this PRP to design PRF. So for example, we can try to first get an Even-Mansour cipher using the random permutations, and then use this Even-Mansour cipher, for example, in the Sum of Permutations, then to get a PRF. But we know that the Sum of Permutation is n-bit secure. However, the Even-Mansour construction is just Perceval secure. So which means if we just plug in the Even-Mansour construction in the sum of permutation, then actually we will get a birthday bound secure PRF. So it's not really something that we want. One way to solve this problem is by considering two rounds of Even-Mansour. Then we will have 2n divided by 3 bit security. However, then the resulting construction will have 2n divided by 3 bit security, but the resulting construction will be twice as expensive as before because we use 4 permutation calls instead of 2. So this means dedicated proof is really necessary. So this is this is actually the main result of this paper, the sum of permutation and sum of Even-Mansour construction, which is actually the combination of sum of permutation and Even-Mansour construction. So we see that if we use the Sum construction with with 2 identical permutations and 1 ambit key, then the resulting construction will be definitely not secure because the 2 y values will just cancel out each other, and then the output will always be the same, which is always the used key. Now, suppose we use 2 identical permutations and with 2 independent keys, K1 and K2. This construction can still be broken in the birthday bound because as long as we can find 2 collisions between 2 construction queries, then as long as this equation happens, then the output of those 2 construction queries will be the same. So the collision can be found in the birthday bounds. Then we are again there will be a relation between the output of the construction query. Then we are able to distinguish the real world from the ideal. And the next construction, where we consider the Sum construction using 2 independent permutations and 1 ambit key. And this construction can still be broken in the birthday bound because as long as we can find the construction, as long as we can find the collision between the m value of the construction query with the x value of the primitive queries, then there will be a relation between the output y1 of the first primitive oracle and the output y2 of the second primitive oracle, and there will be a relation between y1 and y2 with this the c value of the construction oracle. So this construction can again be found in birthday bounds, so very easy to create the construction. And now the last construction, which is actually the most important construction of this paper, the sum construction using 2 independent permutations and 2 independent keys, K1 and K2. And this construction achieves 2n divided by 3 bit security. And we also provide a tag to show the tightness of this security, security bond. And the idea is very simple. As long as we can find a collision between the m value of the construction query with the u value of the first primitive query, and at the same time, the m value also collides with the x value of the second primitive query, then we can break this scheme. So the probability that those 2 equations happen is 2 to the power 2n divided by 3. I mean, it happens in 2 to the power 2n divided by 3 queries. So the security proof of this construction is actually quite complex to explain here. So I'm just going to explain the basic idea. And we use Bertrand's edge coefficients technique to prove the security. The proof is actually the first iteration of Bertrand's mirror theory, with only difference that the adversary gets access to the underlying primitives. So if you are interested, you can read the paper. So now you may wonder if, so we see that for from this construction, we use two independent primitives and two independent keys. You may wonder if it's possible to get a construction with just one single ambit key. So we answer this question positively by introducing the next construction, the SoKAC construction, which is a sum of key alternating ciphers. So this construction can be seen as the EDMV construction by Menke and Memphis, while instantiated with the Even-Mansour cipher. And it can also be seen as the sum of a two-round key alternating cipher with the sum of one-round key alternating cipher, where the first permutation of the both key alternating ciphers are the same permutations. So then we actually get a construction using two independent permutations and one single ambit key. And then we are able to show the 2n divided by 3-bit security of the construction. And attack is actually very similar like the attack used by the SOM construction. So I'm not going to explain it here anymore. So the security bonds is 2n divided by 3. The proof is also very similar to the SOM construction with only difference at the bad events. So we analyze the bad events by using the sum capture lemma. And so we consider the last open problem of the PRP, PRF, RP, RF conversion by introducing the SUM and SoKAC constructions in this paper. So the results achieved here is that we know that there cannot be beyond Berger-Bond secure PRFs using just one public permutation code, and we designed the SUM construction, which is a 2n divided by 3-bit secure PRF, using two independent keys and two independent permutation codes, and we are able to show that the SoKAC construction is also 2n divided by 3-bit secure PRF, while using two independent permutation codes and one single key. So for the future, because we don't know if there can be constructions using two permutation codes where the same permutation is used and one single key. So this can be interesting for the future, and we are not aware if any other PRFs can be designed using two permutation codes, and how the security of the resulting PRF will behave. For example, in the case multiple permutations is considered. For example, if we consider sum of multiple Even-Mansour, so how will the security bonds increase with the number of the used permutations? So this is the end of my presentation, and thank you for your attention.